Okay, I think we might get started. Can everybody hear me? I'll confirm that with Vito.
Yes,
Excellent.
perfectly.
Okay, well, I think we might get started because thank you all very much for attending. We've already got over 3/4 of the people that have registered already connected, so we won't keep you waiting anymore. Welcome to Roctool's webinar. I'm Virginia Lapierre. I'm in charge of communication and events. I would like to thank you very much on behalf of Roctool for your interest in taking part in this event. Just a couple of things regarding Blue Jeans. On the right-hand side of your screen, you will see some information as to where you can ask questions, where the polls will be, and different settings. So that's a good thing to know. We will keep the questions and answers for the event until the end of the webinar, which means after our live demonstration. But we will, of course, take into consideration any questions that you may ask. We are very proud to have Dr. Vito Leo as our moderator today. Vito has 38 years of R&D polymer physics experience, and we thank him very much for being a part of this today. Thomas Vondrak will be speaking as well. Tom has many years of experience in plastics and composite processing. And Mikhail Shally, our head of engineering, who will present the recent studies of flow improvement. Hope you enjoy this next hour. Thank you.
Okay, so welcome. This is Vito from Belgium. I'll be your technical scientific moderator. I'll be watching the Q&A tab as well, and I'll have my own 10-minute slots to give the context, the scientific context and background, explaining the value of the Roctool technology. So let's start immediately by giving hand to Tom, who will present the company in an aspect of the technology.
Well, hello, everybody. This is Tom speaking to you from the northern suburbs of Chicago. So good morning to anyone who's in my time zone, and good afternoon to you there in Europe. If we could go on to the next slide, we want to show you that today's discussion is going to be about flow improvement. We are going to be showing you some live demonstration, also some data off some of our disc and spiral flow tools with a very strong technical backup by Vito regarding why we are able to provide such impressive flow improvement on these tools. If we could go to the next slide. We actually had to do a fair amount of trimming down to come up with a webinar on flow improvement because there are actually a lot of benefits when you start molding with a heated Roctool tool. Those range from easy cleanability of aesthetic surfaces, weld line elimination, micro replication if you're doing some type of micro fluidics, dimensional stability, wider process window, lower molded in stress, cycle time reduction for high heat materials are all benefits that we could have talked about. And if you have interest in those particular areas, please note it in the polls or the questions, and we will likely do it as a future webinar. Thank you. Next slide. Okay, a little bit about Roctool. Roctool is a technology company, and we focus our technology in the area of inductive heating of production tools. We have 190 worldwide patents, and we are a global company. Global in that our staff is from 10 different nationalities. We speak multiple natural languages. We have over 50 plus employees worldwide, and we have over 88 global clients. We have literally tens of millions of parts produced in our high volume production proven methods for heating tools. And we have systems deployed around the world. Currently over 350 system installations with customers producing production parts. We can help bring great cost savings, and we really bring a complete offer. If you look at the bottom of the slide, you can see that we do material and design research. We provide engineering studies. We do the specific design for your components in the tool, and we provide all the components needed to do inductive heating within your tool. We also provide all of the capital equipment. That can be an induction generator and other peripherals such as an interface module and cooling units to allow you to both heat and cool very quickly. And we wrap all of that with great support globally for installation, for process startup, training, and maintenance, so that at the end of our first encounter, you end up with a molder that knows how to use our system and produce parts and solve problems as they come up. Next. Okay, a real quick view of what we call global platforms. What is a platform? A platform is an area where we have agreements that if we need, we can go in and do a molding for a customer on existing equipment. We have certainly many more installations globally than what we're showing here, but we want to let you know that we do a lot of things to help get you started with Roctool molding. In particular, right in the middle, you can see the big R there. We're a French company. So in Les Bourget de l'Arc, France, we have our headquarters. We also have a very detailed molding department there where we can do material characterizations and material studies. But it's not just there. In Asia, we also have many areas where we can do those types of moldings. And in the US, I would highlight we have a new relationship with Beaumont Technologies up in Erie, Pennsylvania, where you'll see in today's show that we're doing some molding in a spiral flow tool, doing some molding in a disc tool, and that is an area here in the US that we can work with this company, Beaumont, to provide those types of characterization. Next slide. All right, let's talk about induction. I would have you concentrate here on some of the benefits of Roctool induction heating versus some of the other ways to heat a tool. And on the first line, you see heating speed, up to 25 degrees centigrade per second heating, really unlimited temperature. We can go up, we say here, up to 1,000 degrees centigrade. That's not necessarily for an injection molding application, but we do some applications where we have heated mandrels and we're doing bending of high heat materials where we can get up there. Very efficient from an energy perspective and really give the widest possible process window for you. Let's compare that to some of the other processes out there. There are flow processes. Now, I don't want this to come off as if we don't use flow processes as well. We actually use flow processes to cool our tools. The thing you should understand about flow processes is they are limited by the thermal conductivity of the tool steel that you're working with. And really the maximum amount of temperature change you can see is up to 10 degrees centigrade per second with a flow process. Clearly, for heating, Roctool can be 2.5 times faster than that. There are other methods out there, such as electric heating. Electric heating tends to be a little bit slower because its resistive heating process needs to go through a thermal barrier to get the heat into your production tool, and that tends to reduce the speed at which you can heat. So next slide, please. Okay, so I know we have a graphic dynamic on the left side. I want to start this slide by having you take a look at the right-hand side, the principle of induction heating, the Joule effect. Roctool brings the right-hand rule to injection molding. What is the right-hand rule? If you look at this diagram on the right-hand side, you see the gray arrow. If you align your thumb along that gray arrow, you can see that if you inject a current in that direction, you will create magnetic fields in the direction of your right hand fingers. You can see those as the black magnetic fields shown. So in the presence of ferromagnetic tool steel, those magnetic fields will induce currents running in the opposite direction of the injected current. And so what happens? Current running through steel creates heat. A very simple thing to have in your mind is an incandescent bulb. You turn on an incandescent bulb, you have electricity running through a filament, which is a resistor, it immediately gives off heat. Gives off a lot of light energy also, but I want you to understand that current through a resistor gives off heat. That is the fundamental way that we heat up a tool. The way we generate those currents is through magnetics. And there are very big benefits of using magnetics to generate those currents because we no longer rely on an intimate bond between our inductor and the tool steel. In fact, we need to have a high resistance path. We can't have conduction of electricity from our inductor to the tool. Because of that, we can transfer energy very quickly through magnetics and convert it into heat energy quickly. I'll now have you look over to the diagram to the left. Now, unfortunately, it's not dynamic anymore, but I'll talk through it. What you should see is two sets of holes. And I assume Virginia's going to go back and hopefully we get our dynamics back there. So we lay out in injection molding closest to our cavity surface, our inductor network. And you should see that the inductor network heats up that cavity surface very quickly. We then, after we've turned off our inductive system, after our cavity has reached our target temperature, we will wait a few seconds for the energy we've dumped into that tool to conduct out to the cavity surface. We will inject our plastic, and then we will go into our cooling cycle. What you should notice here with cooling is that we have the ability to change the flow rate of that cooling relative to the cycle. We don't always do that, but I want to highlight that we do have the capability to do that. The other thing I would highlight is you are looking at a two-network system. You have the ability to have completely separate control of your dry heating network and your wet cooling network. That lets you have the great benefit of using colder cooling water and really helping you get some better cycle times on higher temp materials. Next slide, please. All right, here's a quick layout of a Roctool system. I'm going to work from the right to the left. It all starts with some capital equipment, our generator. And every generator needs to have its own cooling unit. That's to provide a stable waveform for the energy we're putting into the tool. Just to the left of the generator, you see our control unit that interfaces with the press. It also interfaces with the custom design network that we have built into your production tool. And it turns on and off our heating system as you need it. And then as we move further to the left is what we refer to as a performance cooling unit. And that gives us the capability I highlighted in the previous slide of being able to not only have colder water than you would in conventional, but also to be able to modulate the flow rate, going from one extreme of purging while we're heating to low flow, to moderate flow, to high turbulent flow when you want it. Okay, that was very quick. Hopefully you've got an understanding of induction and how we implement it. And I will now turn it over to Vito.
Welcome back again to Belgium, warm and dry Belgium, I guess, as most of Europe right now. I'll take just one more minute to introduce myself a little bit better. So as Virginia said, I've been active in the industry for almost 40 years. I'll be retiring from that job very soon. But I've also created a training company, and I really specialize in injection molding. Maybe some of you have already taken my courses, and very recently I started an online platform, try to still work on training in these difficult times. I have 2 slides which are essentially taken pretty much from my courses, and I will use those 2 very simple pictures and graphs to explain the value of this induction heating approach and why it works so efficiently, effectively. You see a cross-section of a classical molding, and of course you see here the flow front with fountain flow, but I want you currently to focus on what we call the frozen skin. So whenever you mold, conventional molding, your mold temperature would be somewhat below the glass transition if it's an amorphous material, and certainly below the melting temperature if you're molding a semi-crystalline material. In both cases, it means that the contact between the melt and the steel of the tool will rapidly form a thin frozen skin. Now, it turns out that this frozen skin has a variable thickness. First of all, it's not going to be the same everywhere throughout your cavity. And of course, it will vary also over time. It is, of course, extremely sensitive to mold temperature because that is the dominant boundary condition to be taken into account. But it's also extremely dependent on the injection speed. Because obviously, if you fill your cavity in a fraction of a second, you literally have no time to move the heat from the steel, or rather from the plastic to the steel, which means that you will not have time to grow much of a frozen skin. So it's a very dynamic problem. But let's say that you typically end up with some sort of thickness, which I'm calling small h here. Now, what is the order of magnitude of this? It's not uncommon at all to be between 100 and 200 micrometers. So it's 0.1, 0.2 millimeters. It's fairly typical. Now, you can imagine that if you're molding a 3 millimeter thick part, losing 0.2 millimeters of flow channel on each side is not going to be a dramatic loss. But if you're trying to make a part of 1 millimeter thickness, or maybe even lower than that, then you have a substantial effect of this reduced effective thickness, because obviously if we start looking at the effective channel for flow, it's going to be the nominal thickness minus 2 times the frozen skin. Now, it's interesting to go back to some of the fundamental physics. Now, physics shows that if you keep everything else constant for a given filling rate, a given viscosity, the pressure drop that you have to fight against, or the pressure you have to provide with your molding machine to fill a certain given cavity, is proportional to the reciprocal of the third power of the thickness. Now, if you have a frozen skin, this H is actually H minus 2H, of course. It's the effective channel. I like to use a sort of simplified approach. If we kind of linearize this and think in terms of percentage, from this formula, we can say that if 10% of the channel is blocked by the frozen skin, that will give you a pressure increase of about 30%. That's because of the cube. So it's just a sort of linear approach of this complex formula. So every time you lose 10% of effective thickness, you need to add 30% more pressure. So you see it's a very, very strong effect. And if you can somehow reduce the frozen skin, of course, you could then a huge benefit. Now, again, 10%, 200 micron is 10% of 2 millimeters. Then you have one frozen layer on each side. So with 100 micron on each side, you lose 10%, 2 millimeter plate. But if you're struggling to make a critical, maybe medical part that has only 0.8 millimeter thickness, you are losing much more than 10%. So you will see an increase in pressure to fill that could be 50, 60, 70, 100%. So a very strong increase in pressure. Of course, you could run your mold much hotter, but as you know, it doesn't make sense to run it really hot with a conventional flow process because the timing gets completely off and the economy collapses. Now let's move to my second and last slide to illustrate the benefit of this process and the value and why it is so useful. The easiest thing to do is to go back to a very old plot. For those who have been around for a while, they might remember that this was the single plot, the only plot Moldflow was capable to produce 35 years ago, well before finite elements. So it was pressure to fill a cavity as a function of filling time. And it typically looks like a U-shaped curve. So what this means is that if you want to fill very fast, well, you need to push a lot. That's basic mechanics. You want to go fast, you have to push hard. As you decide to go to slower filling rate, you need less pressure, okay? So you can fill your part with less pressure. But all of a sudden, in classical, normal cold mold, injection molding, you will experience this dramatic upturn at some point. So the slower you go, suddenly, the more pressure you need. Now, where is that coming from? From the frozen skin. Because we are going slower, we give more time to the melt to freeze off. The actual thickness of the frozen layer will be higher, so the percentage of blocked channel will be correspondingly higher, and the pressure will go up. And it goes up so dramatically that you reach a point here where you produce a short shot. So there's no way to fill your cavity, and that's why there is a concept of minimum filling rate, and there is a concept of optimum filling time, which you could identify as being, say, the minimum of this curve. Now, if you do this experimentally with a given part in front of your machine, you may not be able to get the full curve, and Michael later on will show you some results. Depending on the part thickness, you might be highlighting more the left side of the graph, or maybe you may be watching more the rising right side of the graph. But in theory, it's a full U curve. And an interesting concept here is the processing window. You could say that by looking at this width, you have an idea of how much you can play with the filling time and keep the pressure at reasonable values. And it is important to understand that this processing window will be dramatically changing with part thickness. Let me just put up a little graph. If you're molding a very thin part, this processing window becomes extremely narrow, so the pressure will be very high, and the precision needed to fill the part in terms of filling rate, it will be dramatic. And it's so typical for very small critical medical parts that people have found that, for instance, they can optimize this in a single cavity cold runner system, but when they move to a multi-cavity hot runner system, they have a problem because of the compressibility in the hot runner. They cannot match the required filling time. So the problem there is your processing window is far too narrow, and it makes your life extremely difficult. Now, before I turn the microphone to Michael, who will show some results, let me show you on this sort of theoretical U-shaped graph what happens if you are able to use a very hot mold. Now, this is somewhat optimistic, and to be honest, it corresponds to a mold temperature equal to your, say, melt temperature. Okay. In this case, you have absolutely no frozen skin. You have no melt cooling near the edges, and that will give you this sort of hyperbolic constantly decreasing pressure. So you can go as slow as you wish, and you could say the processing window is now infinitely wide. Now, obviously, that is not reasonable, because despite the efficiency of the induction heating, you cannot really bump your temperature that high. Technically you can, but it wouldn't be such a great idea in terms of cycle times. So classically, as you will see in polycarbonate examples to follow, you would put the mold temperature pretty much at the glass transition, which will allow you to have no frozen skin, but it's still cold. It's still 140 or 45 for polycarbonate. So you will end up with something like this. Okay, so this is a more realistic Roctool-based sort of process, but you see the tremendous benefit in terms of processing window. All right, I'll give the word now to Michael, who will show you actual results on disc and spirals just before we move to the live demonstration. Thank you.
Thank you, Vito.
Sharing. Yep.
So I am Michael Chailly, Head of Engineering for Roctool in France, and I will present you, let's say, numerical studies that typically illustrate what Vito presented you as a global physical concept. So if we take a look on this first study of flow extension, we consider a central disk of 300 millimeter diameter with a central injection, and we inject two different materials. One is two of them being micron grade from Covestro that are used in the medical industry. And we tested different disc thickness ranging from 0.5 up to 3 millimeter. We will not present all of the results, but a brief nutshell of certain results. And in terms of mold surface temperature, we have considered three configurations. So the first one being the reference for conventional molding. The mold surface temperature would be set up at 90 degrees C on both sides. Then we consider that we have implemented Roctool on one side. So on this side, the temperature would start from 160 degrees C at injection start and getting down to 100 degrees whenever we demold the part. And the third configuration would be to heat both sides with the Roctool system with the same temperature profile starting from 160 down to 100 degrees C. Just a small reminder about how the Roctool process is normally configured to work in the injection molding that you can see on the graph on the left. So we start to heat up the mold surface whenever the mold is open and there is no plastic material, of course, in it. And we stop to heat normally before closing the mold. And during the close, we wait a few seconds more just to let the heat diffuse from the inductor position where the heat is generated, as Tom explained you, up to the mold surface. And we tend to inject whenever we get the best thermal homogeneity on the molding surface, so to have the best results in the end. So when we talk about those 160 degrees C down to 100 degrees C over there, we are basically doing only cooling all the time during whenever the material has entered the mold. If we switch to the next slide. So here we see just a basic illustration of the filling behavior. So we have considered one disc at 2 millimeter thickness with one of the two microns. And we have set up a limit pressure from the press, which is 2,400 bars on both sides. And just to summarize in a nutshell, considering about 2 seconds in injection time, we managed to fully fill the disc in Roctool condition with this limit in pressure, whereas in conventional molding, we have this short that Vito mentioned. Just to give you a brief insight, so if we go to the next slide. On this slide, we have the first configuration, which is with a disc of 0.7 millimeter. And we have the graphs that were obtained for the two materials. So of course, with such a thin material, we couldn't fill the full flow length of 150 millimeter, whatever the configuration, because we are reaching this pressure limit. But considering the maximum pressure limit that I mentioned earlier on, we can see that in Roctool conditions, whatever your injection time is, hitting both sides, we managed to increase the flow length for both the materials. In this specific case, about 20%. If we hit only one side with Roctool, the gain is about 10% compared to the conventional molding, which is the yellow curve that you can observe on both sides. So it means that either you could have extended flow length, so possibly injecting longer parts with a single gate, for instance, or we could also reduce the filling rate by increasing the injection time, and this would have a dramatic effect on thin parts, especially for the shear rate that is and shear rating that is generated during the filling. So Roctool can help you to do that. Now, if we go to the next configuration. On this one, we have considered the same disc, but now with a thickness of 1.5 millimeter. So this time, whatever configuration, we managed to fill in the part. But you can observe that we see here, as we have increased the thickness, we come, let's say, to the second part of the U curve that Vito mentioned, that was on the right side. So we see that you can increase. We have increasing pressure with the injection time because of the creation of the frozen skin. So ideally, if we take the material on the left, we would need in a conventional molding that is now in blue to inject as fast as possible for the optimal time being 0.5 seconds or even less. And as soon as we reach 3 seconds, we cannot inject any longer than that because we would have a short shot. Now, if we use Roctool, let's say you just comparing the two-phase heating with Roctool, we can see that keeping the same pressure limit, this injection time can be increased up to 5 seconds. So you have a significant gain in terms of processing window there, and that allows you to have a much slower filling, and in doing so, reducing the number of stresses that are frozen in your materials due to the flow. We go to the last configuration of this study. Here we have the same 2 millimeter thickness for the disc. And again, if we take a look at the graph on the right, we can see that in blue, we have, in conventional conditions, in the blue curve, we have an optimal filling time that would be around 1.1 millisecond. And as soon as we want to inject, let's say in 5 seconds, we have a drastic increase in pressure at switchover because we have increased this pressure by 30%. So typically the range of figures that Vito mentioned. Now, if we get to the two-phase heating in gray, whatever pressure you need to fill your disc from 0.5 seconds to up to 5 seconds stays within the 5 to 600 bars range. So you have very flattened curve with a much less influence on the filling pressure, whenever you change your filling rate. And so in this direction, it gives you a much wider, much more stable process to solve other issues that you can endure on your part. Now we're done on this one and we can move to the next one. So if we go to this second study, which is what was made for the spiral flow, so we have this mold that we have available internally or at partners, where we have this very classic spiral flow. We can use different thickness. In this, in the results I'm going to present you are about a thickness of 1 millimeter. We're using the same microlon material, so the 2530. And we have two pressure sensors that are located within the cavity that you can see through red and yellow spots on the picture on the right. And we compare whatever pressure we obtain and associated field volumes according to a standardized protocol to evaluate what is the gain in terms of flow length for a given material grade with the Roctool technology. So for the injection process settings, we have used exactly the same that you will see on the live demo. So a filling rate at 40 centimeter cube per second, and melt temperature, which is 290 degrees C. And what we do is we feel till the pressure, injection pressure reaches 1,500 bars, and then we switch to a pressure controlled, let's say filling, for an additional 3 seconds. So if we take a look at the results on the next slide. Oh, before going to the results, sorry, just to mention the thermal behavior of the mold. So the comparison was made again on a conventional mold being considered at 90 degrees C. And now you can switch to the next one with the temperature curves. Yes, perfect. So we have this conventional mold at 90 degrees, and we will compare it to what we have in the spiral flow mold, which is two-side heating with Roctool technology. And what you see there is that we start with 160 degree down to 80 degree in this configuration. And typically the curves that you have are the one that were directly obtained from thermocouples located within the mold from the trials. And now if we go to the next one. Here you have this, let's say, first flow extension measurement. So we have the correlation of the filling, the flow form position from conventional conditions and Roctool conditions after this, let's say, dynamic filling and 3 seconds of packing, or I would say static pressure controlled filling after switchover. So typically from the simulation, we could see an increase with this pressure limit at 1,500 bars by about 11% in Roctool conditions. And now you can see on the pictures the real samples, and basically we have gone to up to 23% flow extension doing the real thing. There could be mismatch, I would say, in between simulation and experiment, and it often comes from the material characterization that are available in the softwares. If we go to the next one.
Michael, this is Vito. Just to let you know, we are running a tiny bit late, so
okay,
have to move on a bit quicker, maybe.
Sure. So for the flow extension, we can see that we have a reduced pressure loss during the feeding. So basically, we can say that having the same pressure at injection locations, we gain about 15% on the first pressure sensor and about the same value on the second one. So we have a better pressure transmission during the filling within the cavity. And what is also of importance is to note that when we do this, let's say, static filling, in conventional molding, you've got a drastic pressure drop onto the sensors that are located within the cavity, whereas in Roctool condition, you can still fill your mold and have a higher pressure within the cavity thanks to this hot mold surface. So you are able either to continue the filling or to pack efficiently if you were working on a real part. And if we go to the next one, on this one, you can see that we can also improve this flow length extension, because here we have seen results about 23% at 160 degrees C for Roctool conditions from the conventional one. But we can totally adapt the process settings, and possibly we could go up to the melt temperature, but keeping reasonable values, we could, for this PC, go and use a mold surface temperature at 180 degrees C, and then this flow length would extend up to 40%. So just adding an additional 20 degrees on the mold surface, you double the gain that you can expect. So with this ability to do this only through process settings, you have the ability to optimize whatever flow length gain you would have. And of course, it would also impact the cycle time. So it's just, you can choose whatever best compromise you want just through process settings. And if we go to the last slide. On this one, we have this, let's say, some example of whatever measurement we have run into our facilities. So we have what we call HDP database. So we characterize several materials, dozens of materials we have characterized in terms of flow lengths, surface aspect, gains, etc., offered by the technology. And we can see that we have very various results. So if we have in this graph, the first one, that is the one from the study, so the PCA macrolon, that is the second one from the left. And if we consider a broader view, we can see that if we change the material type, let's say from PC up to, and we compare that to the PEI family, we can see that the gain are not the same. As an average on the PC family, we can say we are about 75% in terms of flow length improvement with the material. On the PEI, which is a much more viscous material, we have this, the flow length absolute value is of course less because of the viscosity of the material, but the gain are more like in the 125% gain. And now even if we focus on a single family, which is the PC1, so the blue one square on the left side, we can see that even depending on the grades, depending on whatever modification polymer suppliers have made to their materials to fit your requirements, we can have different viscosity behavior. So we can have strong variation of material gain. So it is really recommended to run for a given material some testing to evaluate the potential gain in terms of flow lengths for a given grade. And that is something that also Roctool can offer. And now I'm done, and I will let the live demo happen.
So thanks, Michael, and welcome to everybody to our demo center. So today, the goal of this demonstration is to show you how much Roctool can improve the flow using with our technology compared to conventional. So we will use the same polycarbonate that Michael presented you, and with our injection machine. So here we have a 160 ton and our Roctool equipment. Here our thermal regulator, so one for the mobile side and the other one for the fixed side, and our controller. So now let's see our injection mold. So this is a spiral mold flow at 1 millimeter of thickness with 2 pressure sensors inside the cavity from RDJ. So David will start the injection with Roctool on. So if we have a look on our controller, we can see that the mold temperature is increasing and we are waiting to reach 160 degrees as Michael showed you. So the condition for that is to fix on our controller 145 degrees, and then we will wait some seconds in order to have a perfect surface temperature homogeneity. So we inject just now, and the cooling starts, and we will wait to reach 80 degrees for the demolding. On this equipment, we can see the curves of the injection pressures. In red is from the injection machine, and in orange and green from the sensors inside the cavity. So as you can see, we inject at 1500 bars, like Michael showed you during his presentation. And we can see the evolution of the pressure inside the cavity. So then, on our thermoregulator, you can see that we fix at 50 degrees for the cooling. Now we can see with David the parts and which length do we reach. So David? 12 centimeters with Roctool on. So now we will turn off Roctool and start the injection at 80 degrees. So in this case, we don't need the controller, and we can see again on our EDAT system from RDJ the evolution of the pressure inside the cavity and from the injection molding machine. So here you see that we inject at the same pressure from the machine, 1500 bars, and you can see in orange again and in green the evolution of the pressure inside the cavity. So it's clear that we increase without Roctool the pressure drop. So now we will see the part injected without Roctool, and in this case the length that we achieve is 10 centimeters. Okay, 10 centimeters. So to sum up, we can have a look on the part here. So we inject during this live demo at 90 degrees in conventional and at 160 with Roctool. But as Michael showed you, we also have an improvement of the flow if we increase to 20 degrees, so at 180 degrees. So to sum up, with Roctool, you have a capability to improve the flow length, and depending your application, you can choose which temperature is the best case for that. So if you want to know more about this demonstration, don't hesitate to discuss with Virginia. She will share you the complete video. And now it's time for Vito, Tom, and Michael for the question and answers.
Yes, thank you. So this is Vito back. We've had one or two questions, and one that I think Tom could answer here is the one from Leonard, who says, if you are heating both sides of a mold, does that mean you need 2 generators for that?
Hi, yeah, this is Tom here, and I did type in an answer, and I'll give it verbally as well. In most cases, yes. If you are heating in 2 separate zones, one zone being on your A side, one zone being on your B side, you would want the independent control for heating that comes with 2 separate generators. I would say it is possible in cases where it's a very well-known ratio of heating you want between the two zones. We can do a single generator to heat multiple zones. That is less common though, because usually we want to have the freedom to independently control the power on the fly, and we want to give that freedom to the processor to be able to independently control the amount of power going to each generator zone. Hopefully that answers the question, and back to you, Vito.
Yeah, Leonard is also pointing that, of course, we did not stress much the effect, the positive effect of this process on the packing phase, but people who watched closely the curves would have seen that because we are delaying the freeze off of the material, that means you have extended packing time and better, lower volumetric shrinkage overall. I had a question about the U-shaped curve very quickly. In theory, this U-shaped curve exists for all materials. Now, if you start looking at materials with different shear thinning, what really happens if you have a very shear thinning material on the left side of your U curve, when you go faster, the viscosity drops at high shear rates. So the upturn on the left could almost become invisible in practice. Although in simulation, you can always push the filling time to crazy numbers like 0.001 second. And if you do that, you will always see the increase. Note also that as you go faster, you have shear heating. So you have two reasons, shear heating and shear thinning, that usually make the left upturn sometimes difficult to reach, both in simulation and practice. The right hand that ends up with a short shot is always there. If you go sufficiently slow, any material will freeze off and you'll get a short shot. Okay, we had a question here that says, is there heater element and thermocouple inside the mold? Sandeep is asking if we have a heating element and thermocouple inside the mold.
We do not have heaters as such within the mold. We have inductors within the mold that generate some heat wherever they are located, but directly within the steel. So the heat is generated directly into the mold near the inductors and then diffused to the mold surface. And for thermocouples, of course, we have thermocouples within the mold that allows us to control the process through temperature, either to measure it and control the process through time, or to control the process through the temperature.
Yes, there is I guess a very important question from Jazir here, who says, what is the impact on cycle time, given that we're bumping up the temperature? What is the price to pay in terms of cycle time?
If we consider injection, the price in cycle time is very limited, especially because, let's say you heat only one side of the mold. As soon as the mold opens, the part stays on the core side and you are heating the cavity side, for instance. You can directly start the heating when you are demolding your previous part. So you would have finished to heat up the mold whenever you are ready to close and inject again within the mold. So this has no impact. And on the cooling side, you have to consider that the cooling, even if we start from a higher mold temperature, we are using a water temperature that is much lower than what you would use in conventional molding. So this allows to help us to remove more heat from the mold within the same cooling time that you are used to. So normally we tend to be close to the cycle time, normal conventional cycle time. We can be a bit less, a bit more, a few seconds more. Of course, if we get back to the example, and whatever you want to achieve is very high flow lengths, and this is really your objective. And to obtain that target, we increase the temperature of the mold surface up to numbers that are the reason, because if you do not do like this, you wouldn't achieve the part. If we go to very high temperature and large thermal cycle, it takes a bit wider, a longer time, but in conventional molding, you wouldn't simply be able to achieve the part. So it just really depends on your objective.
Yeah. There's another question here. What to do when you have multiple inserts? So the example seems obvious if you have a simple, two-plate mold, but in a complex tool with moving sliders, how would you implement the Roctool technology?
We have the ability to address it several ways. So we could control different inserts by putting like dual zone generator, meaning different zones like we have talked about for the two sides heating of the mold. But we could also connect those sliders together in series. So we would put different inductors in each in each insert, and put them in series and control it via a single generator. So it can be achieved.
Okay, thank you. One more question from Leonard, who asks, how high are the inductors heated, and isn't this heat going to reduce the efficiency of the flow standard cooling system?
The inductors itself is heating a little bit, I would say, because of course it's copper wires, so you've got electricity going through it, and you have a small electrical resistivity, but the increase in temperature is nothing. The main energy that is created is really created within the steel. So basically your steel in your mold around the inductor is hotter than your inductor itself.
Yeah, so it's an induced current in the mold that creates the heating, not the heating of the copper wiring that we're using here. Okay, I think we went through all the questions. So maybe Virginia, you can take over to conclude. Let me say that the demo video in a longer form, as well as the entire recording of this seminar, are available on request. So we ask you to send an email to Virginia. She will make sure you get the proper link to either the recording and or the longer video.
Okay. Well, thank you very much, Vito. Thank you, Michael. And thank you, Tom. And thank all of you very much for being part of this this hour's webinar. I'm just checking the time. It has been an hour. Thank you very much. Any questions, as we keep on repeating, don't hesitate to contact. You can contact me and I can direct your questions or queries onto anyone else in the company. Thank you very much, and we look forward to seeing you again. Thank you.
Thank you. Bye to all.
Thank you.
Thank you.